So welcome back. Now we will be starting our session of paper presentation. This session focuses on side channel attacks, and for this session we have two session chairs. One have joined remotely, Professor Sebastian Berndt, and from the venue, Dr. Vinita Jain. We welcome you all. And during the paper presentation, you can post your question in the chat box in the platform itself, or we can take up the question from the venue itself. So over to you, to the session chair. Thank you.
Okay, welcome everyone to session 4 about side channel attacks. And our first speaker is going to be Simon Doge, and he's going to talk about analyzing masked ciphers against transition and coupling effects.
Yeah, thank you for the introduction. I'll share my screen. Good. So I'll start by explaining in short or sketching the context what the work is about. So this is about proving the security of certain maskings, but taking into account more advanced leakage effects. So that means this effects that we know from the work in CHESS 2018, some effects that work in hardware. So things like glitches, transition leakage, or coupling effects. And the idea is we want to show that a masking is going to be secure against all of these effects, and we're going to do this via linear cryptanalytic ways. So we're going to look at the architecture of the masking itself, of the implementation. We're going to see if you probe this masking, what is it the adversary sees. We're going to translate this as the placing of linear cryptanalytic masks, and we're going to search for trails between. Some notes here is we're going to work only in first order security. This is for ease. We're going to consider that the maskings of our S box are black box. So what that means is we're not going to focus in on very specific maskings of the S box. We're going to try and make those as general as possible so that we include a lot of maskings that are already in the literature. And we're going to prove our security by leveraging the diffusion in the cipher, or the masked cipher. And finally, we're going to, just for ease, neglect the key schedule. So the key is just seen as a constant. So in the probing model, we're going to keep it simple. We're going to say the adversary can place a probe in a masking of either a masked S box or a masked linear layer, and the adversary simply sees a part of that computation. Additionally, we are going to assume that our masking is non-complete. So that means that whatever the adversary just probed in the S box of the linear layer, due to the effect of glitches, we just assume that you do not see all the shares of the input of that function, just from non-completeness. So this already protects against glitches. The next thing we're going to do is we have a black box masking that is secure against glitches. We're going to say, what does this masking need to do in order to additionally achieve protection against transition leakage and coupling effects? Now, basically, our adversary is probing the masking, is getting values back. In order to prove that our masking is secure, we want to show that those values given to the adversary, they basically follow a uniform distribution. Because in this case, the adversary simply sees pure random information. It cannot be related to a secret. However, working with arguments that say our distribution is of full entropy, these arguments are tough. Instead, it's easier to simply take the Fourier transformation. That means we want to show that our distribution, the Fourier transform of our uniform distribution is a delta function, remove the peak. At the center, we want to show that the Fourier transform of our distribution is close to a zero function. And that just means that we're working now with correlations. That means we can work with linear cryptanalytic arguments. This will become clear in a bit, because in examples, we'll see that this linear cryptanalysis will be very, very simple. let's first start with transition leakage. We're going to always consider the architecture of our masking. Consider, for example, the AES in a round-based architecture. We again consider that we place a probe in, let's say, an S-box of that masking. We're going to question, so in transition leakage, the idea is instead of if you probe a memory element, a register, you don't just see the element that is stored in there, you might also see the element that was stored previously. So in this register, so you're going to store a new value, you see the old value and the new value. If you probe this S-box, the previous time those hardware components or resources were used, this was in a round-based architecture, the previous rounds of that AES. So that means if I probe that S-box, I see not only the values running through that S-box, but I also saw the values running through that S-box the previous round. So we just extend our model. Now, how does then this look like in a round-based AES? So as I said before, if you probe this S-box, you see two S-boxes from two consecutive rounds. The question now is, well, I know that the left part, this S-box, gives non-complete information because we have a non-complete sharing. The right part alone would also give non-complete shares. The only thing we got to show is that the non-complete shares given in the left and the right are basically independent. If they have nothing to do with each other, then we know our masking is safe. How do we do this? We use linear cryptanalysis. We're going to see what happens to this left value that we know. If we plug it through the shift rows, the first row does not move. If we plug it through the mix columns, this one value we saw suddenly gets spread over the entire column. We add in a key, which we said was a constant, and we get to our subbytes again. But we see that our red values, this was basically the left value that we saw, does not match the blue value. That just means that from a linear cryptanalytic point of view, we have a zero correlation approximation, and that just means those two values, they were not correlated, and so our masking is safe. This is what we're going to be repeating, but we're going to be repeating it over the case studies present, AES and ASCOM, in considering black box maskings. So we take present, we take a round-based architecture, which just says, let's say if I probe this S-box in blue here, the previous time I saw it was the previous S-box in blue, and we see, well, actually here there is a problem because there is a direct wire connecting those two S-boxes. And now in practice, I don't see this leakage manifesting that badly, but in theory you can see, well, there could be a leakage due to transition effects. So what you need to do, you see that there are a few S-boxes linked up to each other. This is this wire here, this blue wire there, a wire here, and a wire at the end. There I need to add some extra randomness. But good news, I can reuse the same randomness over every round. If I use a serial architecture, everything changes. If I use a serial architecture, then let's say I first calculate the S-box on the left, then the one to the right, the one to the right, etc. The only S-box I can probe that might give secret information is this S-box here. Previous time it was used was this S-box here, but we see that the diffusion layer of present, these two are never linked, and so my masking is secure. That means any non-complete masking of present, first order, that works in a serial architecture is automatically secure against transition effects. We don't need to do anything. And that's a result we know in practice. We know that in practice in hardware, these transition effects don't often occur. And here we can formally show, yeah, in this case, indeed, this will not break the masking. In AES, we already studied what happens if you probe the S-box. We didn't handle what happens if you probe the mix columns. And bad news here is that there is a trail. So if you probe the mix columns in a round-based architecture, yes, there might be a transition leakage giving away some secret information. But we see that these trails always pass through one S-box. So if I place some extra randomness behind my S-box, this leakage would be stopped. And again, the good news is I can use the same randomness every rounds and also for every S-box. So that means I just need to place some randomness behind this S-box, but I can use the same randomness to remask the S-box next to it. Because it would be randomness used solely to protect against transition leakage, not against anything else. Another case study would be ASCON, and ASCON was very interesting because ASCON has a substitution layer that has a non-trivial branch number and a diffusion layer that has a non-trivial branch number. And the first thing is, it is not evident to see that if an S-box has a non-trivial branch number, the masking has the same branch number. However, we found two maskings. We found one masking that indeed has the same branch number, and we found another masking that did not have this. It's just to show this is not a property that easily translates, but it's possible. And because of these branch numbers, no matter what we probe, no matter which architecture you use, whether it's a serial or a round-based, we find that if you have a non-complete sharing of ASCON, so a glitch secure one, it is automatically secure against transition leakage as well. So we find that ASCON was particularly nice in this aspect, at least in first order. We also then included coupling effects. Now, a few things to say is that, so again, the definition of coupling effects is given by this work from Chess 2018 by Faust and co-authors. And it just says that, well, if you're calculating several things in parallel, if you probe a certain masked function, you don't see just that masked function, you might also see some of the functions that are coupled to it, so some of the functions that have been acting in parallel against it. A few things. The first is that, well, coupling effects in hardware, they're not, well, that strong, but we thought of including the effect anyway, just for theoretical purposes. And second is, we assume that there is some sort of domain separation technique available. That means that either, so you have these, let's say, 3 domains here, either you're running them in a temporal non-complete way, so in the first cycle you would calculate domain 1, and the second cycle domain 2, and then domain 3, or you have separate VDD lines somehow to separate your domains. This is just technology we assume is present. The question in our work is, can we define some small number of domains to make and prove that if those domains exist, is our masking secure? And again, the study is basically the same. So if we take our present again, we now need to take a look at a share serial architecture. A share serial architecture just means we first calculate the first output share of the first S-box, the first output share of the second S-box, go through all of them till you went through your whole layer, and then you calculate the second output share of the first S-box, and you go through everything again. Now, coupling effects don't really matter because the only thing that is being calculated in parallel is just one output share per S-box. So coupling effects don't actually add anything new. And if we again include transition effects, we get the same activity patterns as we got before. So again, this architecture in present would be secure against all of these effects from Chess 2018. In ASCON, we found things were not as trivial because what happens now is that if you probe the diffusion layer, you might see another diffusion layer being calculated in parallel. So now there are trails. However, if we remove this idea of a black box S-box, well, then you can say, well, which S-boxes would still be maskings, at least, would secure against this? We find that, well, because the S-box from ASCON is quadratic, we can easily find non-complete sharings. So if you use something like 4 shares, which is the minimum number of shares you need for uniformity and non-completeness, then you can see that this non-completeness can act as diffusion. So if you probe the diffusion layer, you might only see, let's say, the second share because the linear layer is working share by share. I would see the second share of the output of the S-box, but also the second share of the input, because non-completeness exists, you see that looking at the second share of the output and the second share of the output, and the second share of the input, you still miss the first share of information, so you still have security. To round up, we've just analyzed with our security models how maskings can be secure against more advanced leakage effects, so to include transition or coupling effects. And this has been interesting because there has been other work trying to protect against transition leakage as well, but they use gate-by-gate measures. So they make, for example, a multiplier that is secure against glitches and transition leakage. And we find that these measures, they typically have to use a lot more randomness. So they end up using twice as much randomness as a normal masking protecting against glitches. Whereas in practice, we know that's not true. In practice, most of our maskings that are secure against glitches, we don't see much leakage happening in practice. And here we find why. Because most of the time, when you take a particular architecture, a particular cipher, these were already, most of the time, already secure against transition leakage from the get-go. And so we can significantly save on randomness costs. And it would be interesting future work to see if we can build tools to verify these properties automatically from a netlist. And we can do this by using cryptanalytic properties from XOR and AND gates. And we also stumbled into some interesting problems in Boolean function theory, where we said, well, there are branch numbers of S boxes, but the sharings might have different properties. So it would be interesting to see if these Boolean function properties of maskings could be investigated further. But I will stop here.
Yeah, thank you very much for the really nice talk. Are there any questions from the live audience?
Any live questions? So I have one. Hi, Simon. Nice presentation, nicely presented your work. So when you talk about, I just have a small query. When you talk about transition leakage, so like, is it from one layer to another, or we are talking about from an S box to S box? Which type of transition leakage you are referring to?
The transition leakage, for example, I think it would be most clear in hardware in a memory element, in a register. So what happens when you are storing your value back? And then, of course, you need to just see where those registers were used. And you kind of, it's more accounting related, I would say.
Okay, thank you.
Okay, do we have any questions in chat? I don't see them right now. Then I had also a question. So do you have any design tips for people designing block ciphers or masking of block ciphers, such that your solution would be more efficient if they follow some rules or something along the lines?
Yeah, so very interesting question. At first, we wanted to also write on this as well. I'm going to give something, well, we said we were not going to take into account the key schedule, but I think that the best advice we can give is that in side channel analysis, so in symmetric key analysis, the key schedule, there are not that clear rules on it, but of course, the key schedule just runs in your hardware just as well as your state function. So in side channel analysis, you can just pick apart the easiest thing to attack. We find we need some interesting cryptanalytic properties of the state function, but if we find them, they also need to be there for the key schedule as well. And that is something, I think symmetric key cryptographers, it's something newer for them, I would say. So that would be my main takeaway is if there are rules for the state function, also apply them for the key schedule in side channel analysis as well.
Okay, thank you very much. Yeah, then thanks again for the nice talk and for these awesome answers. And then I think we are ready for the second talk of the session, given by Andrea Caforio. And he will talk about improving first-order threshold implementations of Skinny.
Okay. Try to share my screen. Okay. Can you see my slides? So thank you for the introduction. So I welcome you to this presentation of the paper, Improving First-Order Threshold Implementations of Skinny. So I'm Andy, and this is a joint work with Daniel Collins, Onion Glamojanin, and Subhadeep Banik from LASEX/Parser at EPFL. So before we dive into the meat of the paper, let us reiterate some background material. So the Skinny construction is one of the foremost lightweight block ciphers. It is in the same rank as present or gift. It's still a contender for the NIST LWC crown as part of the Romulus AAD scheme, and it processes 64 or 128-bit blocks with a tweak key size of 128, 256, or 384. So due to its prominence in the realm of lightweight block ciphers, Skinny has been put under heavy cryptanalytic scrutiny. But nevertheless, a little effort went into the study of side channel countermeasures, especially threshold masking schemes. And then a review of the existing literature will reveal that, in fact, the only first-order thresholding scheme was proposed in the actual white paper for bit and byte serial sequences. More specifically, this construction is a free share endeavor that computes a single cipher round over 4 clock cycles. This is most likely the optimal choice in the serial setting. But we say that we think that it's suboptimal for round-based constructions, which we'll shortly show through a novel way of decomposing the 8-bit S-box. So by spelling out the details, our work consists of two contributions. So firstly, we introduce a new first-order free share threshold construction over 3 clock cycles with a similar area footprint compared to the white paper proposal, and that consumes roughly 30% less energy. And then secondly, a new first-order 4-share threshold construction over 2 clock cycles that also reduces the energy by roughly 30%. It's important to note here that none of these proposals require additional randomness beyond the initial plain text masking. So let us quickly revisit the properties of threshold implementations. So we say that the decomposition of an n-variable Boolean function f equals to z into a set of s functions f0 to f s-1 such that the sum of those functions is equal to f is a d-order threshold implementation if and only if 2 properties hold, namely non-completeness, so that any combination of at most d functions is independent of at least one input share. And secondly, we also need uniformity, so all input and output shares are uniformly distributed. State the exact number of input and output shares of a d-order threshold implementation of degree t is given by the number of input shares is lower bounded by td plus 1, and the number of output shares is lower bounded by td plus 1 choose t. And then it's important to note here also that a first order threshold implementation of a quadratic function can thus be obtained by setting s at the number of input and output shares equal to 3. For the remainder, we will just assume that d is equals 1. So we're just interested in first order threshold implementations. And then we will bootstrap the sharing of any arbitrary quadratic function via the canonical direct sharing of the function x0 plus x1 times x2. So what is the Skinny S-box? So the Skinny S-box is a cross-connected network of 16 2-input logical gates. We say that x0 to x7 are the 8 input bits, and z0 to z7 are the corresponding output bits. So this S-box can be expressed as an alternating sequence of 2 functions. So we have a transformation capital T consisting of 2 XOR and 2 NOR gates, and a byte permutation capital pi, or bit permutation capital pi. So these two functions are repeated 4 times, whereas in the ultimate bit permutation differs from pi. So again, if you look a little more closely at the output functions of this S box, you will note that that only output set 0 has actually algebraic degree 6. So in the light of this, the Skinny authors proposed the decomposition into 4 degree 2 functions f, g, h, and y, as shown in the figure above. So as mentioned before, so this choice is optimal for a serial implementation, but it naturally begs the question whether a decomposition into 3 degree 2 functions is feasible. So to make our endeavor a little more formal, let us state the following definition first. So we say that a Boolean function f is I-representable if it can be expressed as a composition of I functions, f1 to fi, such that the algebraic degree of each function is smaller or equal to 2. Of course, the ultimate goal is then to show free representability for all outputs of the Skinny S box. So an obvious first approach of finding such a decomposition would be to replicate the Skinny author's technique of cutting the circuit into separate chunks. So in fact, all valid cuts into 3 functions can be enumerated computationally, as shown on the figure to the right, and where we have 3 functions f, g, and h, where f and h have algebraic or quadratic, whereas g is cubic. By doing this cutting, we find that none of the cuts actually yields a decomposition into 3 quadratic functions. Pivot a little bit, or we have to dive a little bit deeper. So let's look at the other bits of this S box, the other output bits. So set 2, set 3, set 4, and set 6 are quadratic. So by definition, they're 1 representable. Set 4 and set 7 have algebraic degree 4, and it's not easy. It's relatively easy to see that they're both 2 representable. And then set 0 and set 1 have algebraic degrees 6 and 5, and again, by definition, they cannot be 2 representable, since the set of all 2 representable functions contains a member of degrees 4 or less. So now we have reduced our problem to the task of finding a free representable description of set 0 and set 1, which would mean that the Skinny S box is decomposable into 3 quadratic functions. So just for time reasons, we'll limit ourselves to the derivation of set 0 only and leave set 1 to the interested readers. So the first obstacle one encounters when working with the 8-bit Skinny S box is the immense complexity of the set 0 expression, as shown here. So it's not really possible to directly proceed on the algebraic level. But we can go onto the gate level. So first we note that the set 0 is trivially 4 representable, as shown in this figure. Here in this figure, each node is a 3-input quadratic function, x, nor, y, x, or z. Then secondly, we notice that the 2 nodes at level 1 and 2 can be concisely merged without breaking the quadratic nature of the output bit e. And thirdly, the 2 remaining nodes at level 3 and 4 can be merged in a similar way as before, so resulting in a decomposition of the Skinny 8-bit S box into 3 layers of algebraic degree 2. Of course, this is a really admittedly short explanation that includes much of the mathematical details that went into this work behind. So if you're into the math, then I would advise or refer you to the actual paper. And then, of course, we can use a similar technique to decompose the S box into 2 functions of degree 3. So having established that, so naturally there's no side channel countermeasure work that is completed without at least some preliminary leakage assessment. So in our case, we chose a double-sided approach. So there's the state-of-the-art Silver verification tool that checks the soundness of mask circuits through netlist analysis. But through the unforgiving complexity of this of a fully masked block cipher circuit, Silver is really only possible, or with Silver it's only possible to computationally verify a single 8-bit S box instantiation. So to circumvent this issue, we also decided to conduct a practical canonical t-test on the full cipher circuit, which is shown in these 2 plots here. So here we note that there's a significant statistical bias for the unmasked circuit on the left. whereas the mask instantiation remains secure with roughly 1 million traces collected. So these experiments have been conducted on the state-of-the-art Sakura X side-channel evaluation board that is hosting a Xilinx Kintex FPGA. So having shown the soundness of our construction, let's actually implement them. So we do an ASIC synthesis using the Synopsys design compiler for free standard cell libraries. So the relatively recent TSMC 28 nanometer process, then the high leakage 45 nanometer non-gate process, and then the a bit older 64 nanometer UMC library. Then we perform power analysis or energy analysis through back annotation on the synthesized netlist. If you look at the table, so we compare the 4 investigated schemes in this work. So we have, for one, the byte serial scheme from the actual Skinny white paper. Then we have the byte serial threshold scheme applied to the round-based implementation. Then our new 3-share 3-cycle proposal and the new 4-share 2-cycle proposal. So we remarked that our 3-cycle construction is similar in area, but significantly reduces the energy consumption. And similarly, the 2-cycle circuit yields a convenient trade-off between area, latency, and energy. Of course, this trend also holds if we go to block sizes beyond 128 bits, for example, 256 bits. So in conclusion, we propose the first decomposition of the Skinny 8-bit S-box into 3 quadratic functions that yields a roughly 30% reduction in energy. And secondly, we propose the first decomposition of the Skinny 8-bit S-box into 2 cubic functions with, again, roughly 30% less energy consumption in the process. And that ends my talk.
Yeah, thank you very much, Andrea, for the nice talk. Do we have any questions from the live audience?
Any live questions? I guess there are no live questions. So I think the presenter is Andrea, right?
Mm-hmm.
Yeah, nice work, Andrea. So I am not very thorough with the area that you have been working. But yeah, you talked about first order, right? So any recommendations for higher orders, like how if anyone wanted to move ahead with the higher orders as boxes? So
the problem with higher order threshold implementation is that at higher orders, the number of shares that are required for having a non-complete uniform scheme is just very high. So usually what people do for higher order implementation, they pivot to other masking schemes, such as what is it called? Domain-oriented masking, where you actually have some randomness that is applied during the computation. But using this, you can lower the number of shares. So I wouldn't recommend doing higher order thresholding schemes for algebraic functions that have such a high degree, because it just the complexity of the circuit just grows exponentially.
So in the future, would you like to work ahead with Skinny 256 or ahead with 382? Right,
yes,
now
because I think it's still the #1 lightweight block cipher in the field. So there's no really a way around Skinny anymore. It has been kind of canonical, has become standard in the field.
Yeah, thank you. So if you have any online questions, you can ask Sebastian.
It seems that we don't have any online question yet. So I have another question. You showed very nicely how you reduced these Z0 thing. Was this all done by hand, or did you use like looking at it and have these inside, or was there some kind of algorithm that you used?
So at first we tried to do it computationally, but then we saw that just by cutting the circuit, it's not going to work. So then we just looked at it. Yeah, it was done by hand, basically. Yeah. So we actually looked at the output bit of those functions and looked what happens if we can like shift them to other layers. What does it mean for the resulting equation? And then we found that actually if you shift one of the nodes one layer further, then actually the degree stays the same. And then since the degree stays the same, you can have more leeway of messing with the others as well. And then this kind of like iteratively to this decomposition.
Yeah, okay, thanks. So that's impressive doing that by hand. So, and do you know whether you can like generalize that for other S-boxes, other ciphers, this approach of like shifting things to the top, or is that only applicable to Skinny or to the Skinny S-box?
So it could, the nice thing with the Skinny S-box is really it's kind of forgiving because it's only 16 gates. And I'm not aware of any other S-box that can be represented in such a concise way. 8-bit S-box, of course. Of course, if you do this for 4-bit S-box, it's not really interesting. But 8-bit, I think Skinny is one of the only one which has such a concise description. If you want to go to, for example, the AES S-box, it's really hard to describe, and it's almost like 100 gates or something, 2 input gates. Of course, you can try, but I guess it will be much harder. Yeah. So there's still work to be done in kind of generalizing this approach.
Okay, thanks a lot. We still don't have any questions from the online audience, if I'm not mistaken. So if I understand correctly, then the Skinny authors presented that you had 4 quadratic S-boxes, right? And then you improved that to 3 quadratic S-boxes or 2 cubic S-boxes. And is your 3 quadratic S-boxes approach clearly superior to the 4 quadratic S-boxes, or is there something? I mean, I saw that the area was slightly larger, but only very slightly, right?
The area was slightly larger, but the latency is much better. Instead of doing 4 cycles, you do now 3 cycles, right? And then this has the nice side effect of less power and then less energy, of course. Or less energy, let's say. Just an energy reduction because the Cipher is not running as many cycles as it would with if you look at the Skinny, at the approach they use in the Skinny white paper.
So basically, there is nearly no drawback from that perspective on using the 3
that's
S-box.
nice. Yes.
Oh. Okay, that's really nice. Okay, if we don't have any more questions, I think we can go to the next speaker. Andrea, thanks again for the nice talk and the explanations to my questions. Yeah, and now we have a live talk given by Nilanjan Datta. And the talk is about elastic tweak framework for short tweakable block ciphers.
Fine, right? Fine. ঠিক আছে, ঠিক। Is it visible?
Yes, it is.
It should be fine. Okay, thank you, Sebastian, for the introduction. So I'll talk about this elastic tweak framework for short tweak TBC. This is a joint work with Dr. Avik Chakraborty, Dr. Ashwin Jha, Dr. Patemak Manselias Lopez, Professor Mridul Nandi, and Dr. Yu Sasaki. And just one disclaimer that this paper is basically on symmetric key cryptography, not exactly on the side channel aspects. Okay, so let's start with tweakable block cipher. So as we know that tweakable block cipher is a basic building block that is similar to the block cipher. So what it takes, so consider it is a function or that takes a key of size say k bit and a block of size n bit, and alongside that it takes a tweak of size t bit, and it outputs n bit block. So basically the property that it holds for this tweakable block cipher is similar to the block cipher, but here instead of having just for fixed key in block cipher, we have for any fixed key ek is a permutation over 0 1 power n. So here we have for any fixed k and t, ekt, that should be a permutation over 0 1 to the power n. And for tweakable block ciphers, we wish to have this tweakable PRP security. That means that it should be hard for an adversary to distinguish a random tweakable permutation from this construction. Okay, so tweakable block ciphers are widely used in symmetric key cryptography. So it has several applications in designing parallel MACs like PMAC, parallel authenticated encryptions such as OCB3, COPA, COM, and several hash functions also use this as the basic building block. And it is also used in key derivation functions and disk encryption. Okay, so now let's look at some other applications where tweakable block ciphers may be of use. So I'll talk about 3 of such applications where tweakable block ciphers may be a very good solution. So one of them is reducing the key size. Second one is design simplicity, and the third one is efficient short message processing. So let's see one by one. So in reducing the key size, so one can use multiple keys in block cipher based mode. Now use of multiple keys may boost the overall security, and if you use multiple keys, then you can simplify the overall analysis of the constructions. And however, the problem with using multiple keys is the state size increases because you have to store all the keys. So one possible simple solution is to use a single keyed Tvc and use a single keyed basically tweakable block cipher, where instead of different keys, so instead of different keys like this K1, K2, Kj, you use a single key K and use different tweaks like 1, 2 up to J. So this may be one solution. So one possible straightforward applications is something like this. So you consider this FCBC construction. So it uses 3 keys. So one key is K0. So all the intermediate blocks are encrypted with K0. And for the last blocks, depending on whether it's the full block or a partial block, you use a key K1 or K2. So instead of this, if we have a TBC, we can use different tweaks for that. So use same key K and you use tweak 0, 1, 2. So basically you can have a similar construction like FCBC, and we may call it as TweFCBC, which is single keyed, and it gives better security. So better security means this is giving actually security as comparable to this FCBC. And there is a construction similar to FCBC, but that uses single key, that is called CMAC, that has a weaker security. So here with TweFCBC, you can achieve both single key and the same security or as compared to FCBC. Apart from that, you can use this TBC for design simplicity. So if you can look at this clock authenticated encryption, so just consider on these functions. So for this authenticated encryption, you need several domain separations, and for that you need several small linear functions. So like this I and H, and you also need this fix 0 operation. So this fix 0 basically just fixes the most significant bit to 0. So you need these operations. So this is for the AD processing. Similar, when for the ciphertext generation, you need to apply this fix 1 function. And while tag generation, you need this G1 And here you need this F1 and F2, these linear functions. So the design actually gets very complicated. And when you analyze them, the security analysis also becomes very complicated because of these several kind of these functions. And you need to take care of several bad things. So instead of that, what you can do, instead of using this AF, G1, G2, H1, H2, and these bit fixing operations, you simply use a same key and just use different tweaks to separate the domains. So that will actually give you a very good modular design, as well as simplifies the security proof as well. Now, third application is efficient short message processing. So there are several applications like applications in Zigbee or low Bluetooth energy. So these applications of these, then there are CanFD. So in these kind of applications, the message size is very small. So it's typically ranges from like 128 bytes. So in such cases, what you can do, you can use something like this light Mac. So this is a very fast Mac, but what it has problems. So they use 3 keys. Again, you can see there is K2, K0, and K1. And here you append this, the block length. So here you append this 1, 2, this block length with this message. So that actually essentially reduces the rate of the construction. So again, what is the rate? So rate is basically number of blocks you processed for this message. So number of bits is you process per primitive call. So if you use a 64-bit block cipher and say you want to process a message up to 500 KB, so 500 KB, that will actually, if you just plug in it into bits, so it will be something like 2 power 22 bits and 64-bit block, so roughly 2 power 16 bit. So what you have, so you have to devote 16 bits here to have this to accommodate these lengths. So what you will have, so the message size will be 48 bits. So whatever the rate would be something like 48 by 64, that is 3 by 4. So you basically reduce the rate, and as well as you are using 3 keys. Instead of that, what you can do, you can simply use different tweaks for all the blocks. So here you have 2 separate tweaks for the finalization. You have tweak 0 and 1, and you use different tweaks for all these blocks. So you can see this 2, 3 up to L plus 1. So this way you can process, and that will actually gives you a single key construction, as well as this gives you full rate. So you can actually accommodate the full 64-bit, or you can inject basically 64-bit messages for each nonlinear calls. So this basically gives you a motivation. So now what I'll talk about is basically existing TVC designs. So there are several TVC designs, but they have some shortcomings. And to overcome that, we'll propose elastic tweak framework, and we'll just demonstrate 2 simple instantiation of this framework. One is 2E AES and one is 2E gift. Of course, from the name, you can say that this is a variant of AES and this is a variant of gift. And finally, I'll conclude with the significance of this one concrete example that will actually demonstrate the significance of this work. Okay, so let's look at some TVC designs. So one TVC design is proposed by this Rogawe and Rogawe et al. This called as this XE, that is XOR encrypt, and this is XOR encrypt XOR. So here you can see, so the message is XORed with some masking state delta, and this delta is basically generated using this L. So L is basically an encryption of 0 or nonce, depending on the construction. Similarly, you can define XEX, and based on this XE and XEX type, we have several popular authenticated encryptions such as OCB, COMB, and there is the second framework that we have is for TVC design is this Tweaky framework. So what it takes, it uses a iterated key alternating approach, and here tweak and the key are processed together. So that defines you this TK. This is basically consisting of this tweak and this key, and you just apply some linear functions on this to update this, and again you apply some linear function on each of the updated functions, and you inject it in the state to define the ciphertext. So this is another framework. So these are the basic popular frameworks for TVC design. Now, both of these framework, there are some limitations. So for XCX, you require an additional block cipher invocation, which may not be very good when you process very small messages, and you have some storage over it because you have to store that secret delta value. And typically this XCX construction, a general weakness is it basically degrades to birthday bound security. So you cannot achieve more than birthday bound security if you apply this XC or XCX kind of construction. And for tweaky constructions, the tweak schedule is typically quite costly, and it is very difficult to optimize for short tweaks. And you need basically you need to increase the number of rounds, and that will actually affect the throughput of the whole cipher. So basically what we want, we wish for this domain separation and short message processing, we want to have a tweakable block cipher that can handle the short tweak very efficiently. So in that respect, we propose this framework called Elastic Tweak that basically captures elastic expansion of short tweaks, and we typically consider tweak size of 4, 8, and 16 bits. And this is basically a generic framework that converts any SPN-based block cipher to a short tweakable block cipher that we call 2EBC. So let's say the block cipher 2EBC. So we can convert according to this to 2EBC. So let's look at the design basic overview. So what do you have? You have, this is a short tweak. You expand it to a long tweak. And what you do at a certain interval, you inject this long tweak in after certain interval. So for AES, maybe after 2 rounds, you inject this whole tweak into the state. Fine. So you just inject the same extended tweak for everywhere. So you can see this TE is basically injected. So this block is basically what we have extra on top of the block cipher construction. So the lower part is basically demonstrates the block cipher construction, and this tweak injection is basically demonstrates the, making it tweakable, short tweakable block cipher. And so how do you make the expansion, tweak expansion? So we use a very simple algorithm. So you just XOR all these words. So here you have several words. So say how many words? So each of say W bits. So you just XOR all of them. You expand the tweak and make it of just double the size. You just have all these values, and you just put this XOR sum. You just XOR with each single words. So typically you can see if you have 2 tweaks differs in just one word, after this tweak expansion, it will definitely differ in at least 4 bits. So that actually gives you a high distance encoding. And then if you require, you can make optional copy of this same expanded tweak. And the basic rationale is you generate the high distance code with extremely low cost, because you just need to have this very small number of XOR operations. And how do you make the tweak injection? So we'll basically follow an uniform tweak injection. So tweak will be injected at a certain or at a fixed interval, and the same expanded tweak is injected in all the cases. And so where exactly do you inject the tweaks? That actually is completely design specific. So you have to affect certain number of S boxes depending on the design. So that is depending on the design. And what you have, so because we use a linear kind of expansion, so the short tweak TBC that we denote as this small TBC, so instead of capital TBC, so TBC with 0 tweak, that is essentially same as the block cipher, because we use linear expansion. And what should be the security performance trade-off? So this should be that we should have that this TBC should have similar security level as the underlying block cipher. And the performance requirement is you try to minimize the expanded tweak size that will give you area efficiency, and you try to maximize the tweak injection interval that will give you energy efficiency. So you now, depending on a construction, you properly estimate what should be your security performance trade-off. So you must achieve this security level using, and you try to have as you try to improve this area efficiency and energy efficiency. So this is the basic security performance trade-off for this elastic tweak framework. So let's move on to concrete instantiation. So from AES, we have defined two AES. So all the operations are similar to AES, except this optional add round tweak. So in add round tweak, what we do here we have three variants. So for the first variant, you take a tweak of size 4-bit, you expand it to 8 bits, you inject the tweaks in the first in the first 8 edge box. So by first 8, we mean the first 2 row-wise edge boxes. So you inject those tweaks in those edge boxes, and you inject those tweaks at an interval of 2 rounds. Similarly, you can define AES variants with 8-bit tweaks and 16-bit tweaks. And how this round 2 or this number of affecting edge box depends, that actually depends on the security performance trade-off. So that is basically determined using that trade-off. And so here is one implementation result of AES and 2EAS. So the basic thing to point out is, you can see for AES and 2EAS, the area overhead is very, very minimal. So from 1605, if you have 4-bit 2EAS, it's 1617, for 8-bit 1632, and for 16-bit 1659. So you can see with a very minimal area overhead, you can actually implement the tweakable variant of AES. Similarly, you can use it for the gift. Again, similarly, you have the same operations of gift, but you have an optional add round tweak. And here are some variants of gift that we propose. So this first one is defined on 64-bit, and this takes 4-bit tweaks, expanded to 16. Then it affects basically 16 edge boxes, and you inject the tweak after 4 rounds. Similarly, you define for this gift 128 with tweak size 4 and 16. And how do you choose these tweak injection positions or this gap? Again, depending on how your security performance ratio works. And for this tweak injection position, we basically actually inject the tweaks in the least significant bits. This is primarily because the key addition or the round constant addition, they are not actually added in this least significant bit. So that those doesn't cancels out. This is why we actually follow the rule that we will inject the tweaks in the least significant bits. So this is more or less, and similar to AES and TWE-AES, we have, if you look at gift and TWE-gift, you can have the similar results. So here 449 to 479, and here 763 to 796 and 805. So with a very minimal area overhead, with cost of very minimal overhead, you can process short tweaks. And so now moving on to the significance of this result, and this can be seen from 2 well-known construction, Sunday and Estate. So Sunday is a authenticated encryption following this MAC-DEN encrypt type of mode. So this is kind of a CBC MAC kind of mode, and then you have a OFB kind of encryption mode. So, and here in this mode, you need a constant encryption at the beginning for the security of the mode. And a just tweakable variant of this construction can be made by Estate, that is proposed by us in this NIST lightweight competition. And here you have different tweaks to process all the domain separations and this initialization. So for initialization, you use some tweaks. For all the intermediate blocks, you use some tweaks. For the final blocks, you use some different tweaks. For the final message processing block, you use some different tweaks. So this way, you can just vary over these tweaks to have the similar design as Estate. And what you gain, so for Sunday, this is Estate is basically gives you an energy efficiency because it requires one less block cipher invocation, because that constant block cipher invocation is now you can remove, and the overall design becomes simple. So for Sunday, there are use of several constant multiplications with 2 and 2 square. So you just remove those. You can perform the same thing with just different tweaks. And Sunday was shown to be int RUP insecure. So if you release unverified plain text, then Sunday is an insecure construction. So for Estate, we prove that it is actually gives you this additional security under releasing unverified plaintext. And if you look at the result, this is where the significance come. So from gift to tweak, the area improves slightly, but because of the design simplicity and overall this block cipher minimization, you actually have the overall area of the whole construction is reduced. And of course, we have a better throughput. So it's kind of not a trade-off of area and throughput. So you have a gain over in both the direction, which is really significant because you are minimizing the area as well as improving the throughput. So this is where the beauty of this short tweak TBC comes into picture. And also you can show that for when you consider short messages, the throughput is quite high for when you consider this, you apply this state with say 2 AES, while in case instead of applying AES with Sunday. So you can see that the throughput is quite high for short message processing as well. So this basically gives you the main significance of this having this short tweak TBC in our life, and you can see that this actually gives you a very significant improvement in several designs. So that is more or less what I have, and I'll conclude with this. You can use also in other applications, like if you use multiple algorithms on same platform sharing the same key, then the security may not hold, because if you use same key for 2 different algorithms, but with short tweak TBC, you just use different tweaks with the same key, and you can just have the same key for various and for running several applications in one platform. And so whatever this elastic tweak framework, this is basically for, we have constructed it for SPN based structure. So extending it to ARX based constructions, and this designing short tweak TBCs for public permutations maybe are some good future direction problems. So that's all. Thank you very much.
Okay, thanks a lot, Nilanjan. I fear that we ran out of time for questions. So as far as I understand, there is a 15-minute break where you can ask questions and answers. There will be a shared Google Meet link.
Yeah, sure. So if you have any questions, just ask me in the Google Meet.
So any live questions?
Yeah, just one.
Yeah.
Sure.
So do you mean to say that by using a single key and several tweaks, the security will always be maintained?
Yes.
Always.
Yes, that will be maintained, because that will be taken care by this short tweak TBC, this TPRP security requirement.
So I have a question.
Yeah.
So here you are talking about, like, we are using, you are saying that you are using tweaks in the keys. Okay, so
tweaks out of keys.
So I got it. You have proposed a block cipher technique where you are talking about, area efficiency and throughput.
No, so we are basically, this technique is basically taking a block cipher as input, and you are generating a short tweakable block cipher.
Yeah, so like the pattern that you are using to produce a tweak, for example, zoring and then placing it at uniform places, is very uniform, like, very predictable. And nowadays, there are already problems with symmetric key cryptography. We all know it is, prone to a lot of type of attacks and all these things. In that scenario, do you feel that the tweak thing that you have proposed is actually resistant against those type of attacks, or, key guessing and all those things?
Yeah, but those are already taken care of in the cryptanalysis part.
So when you implemented it in AES, you analyze the security, or you just talked about area and throughput?
No. We also taken care of this 2 AES. So cryptanalysis result on 2 AES. So like differential cryptanalysis, you don't work for AES, but for 2 AES, if you use different tweaks, so there is a differential cryptanalysis. So we also gave a sketch of all. So
you have added that in paper, because I could not see in the presentation.
Yeah, so that actually, because we have some paper limit on the paper, so you can actually find it in the full version. So in the full version, all the cryptanalytic results are already specified.
Oh, okay.
Possibly we have also, in this version, we have referred to the full version that you can have all the cryptanalytic results up
So
there
where
in
you
the.
are publishing your full version?
This is already published in ePrint. You can already access it
Okay.
with the same title.
So, thank you. So over
Thank
to
you
you,
very much.
Sebastian. You have any online questions?
I don't think that we have any online questions.
So maybe you can ask if you have, or put any concluding remarks.
I think then, in order to have time for the questions in the Google Meet, we are done with the session. Thanks again, Nilanjan. That was a very interesting talk.
Thanks.
And also thanks again to Simon and Andrea for their interesting talk. So that finishes our session about side channel attacks. And now we have these Q&A. If you have questions to the authors, please join the Google Meet. And otherwise, we have a tea break of a few minutes, and then we start at 5:15 p.m. in IST to talk about false attacks. Okay, thanks again to all of the speakers. Thanks again for all of the questions, and see you later.